Hello, today we're going to talk about representing relations and functions. So our essential question is how are functions distinguished in various representations? So before we talk about functions, we want to first talk about a relation. And a relation is any mapping, pairing of input values that will map or pair to some output value. And a relation can be represented first as an ordered pair. So for example, the first ordered pair listed is -2, 2. That is mapping or showing a pair between our input x, -2, and our output y, which is 2. So that ordered pair right there is a relation because x and y are related to each other. We could use a table. For every x pair that maps to a y pair, you have a relation. So -2 maps to or pairs with 2. -2 maps to -2, 0 maps to 1, 3 maps to 1. So all of those are examples of a relationship or a relation because each x has a corresponding y value. You can use a graph. So every point that's drawn on the graph also represents a relation because every input value has an output value. And then a mapping diagram. So a mapping diagram is saying if -2 is my input, I'm going to follow this arrow over to -2 on the output. And that maps or illustrates the relationship between -2 and -2. So every value on the left will map or pair to a value on the right. The domain is the set of all input values in a relation. So you can think about that as the x value or the input values. And then for range, that represents the outputs or the y values. And then again, that same example from the previous slide is on here of a mapping diagram. So what it's saying is everything in the input column on the left here represents the domain, what we put into the function, and then everything underneath output, these all represent the range or the y values of a function. And then what is a function? So you can have a relation between any sets of ordered pairs that you want, between any x and y input output that you want. But if it's going to be a function, that means that every input value has to have exactly one output value. So we have a few examples on this page. I'm going to look at example A first. Is this a function, why or why not? So for the input column, I can see that -2 maps to -1. And -2 has exactly one output value. So that's good. I can see that -1 maps to 0. -1 has exactly one output value, so that's good too. I can see that 3 also maps to 0. And that's okay if you have more than one input going to the same output. It's that every input has to have exactly one output, even if it's not unique. So 3 maps to 0, and that's okay because we still have that same condition met. 6 maps to 4, that also works. So every input on the left-hand side has exactly one output on the right-hand side. So this is a function because all inputs have exactly one output. And then looking at example B, I can see that -2 maps to -2, perfect, meets the conditions. 1 maps to 0, okay, 1 has exactly one output and that's 0, so we're good to go. I can see that 2 maps to 2, and then 2 also maps to the number 3. So this is actually not a function, it's just a relation. Because 2 has more than one output. So that's how you can tell with a mapping diagram. And then if you're given a set of ordered pairs, number 1, you can just plot the points and check and see if any of your x values show up with more than 1 point. Another way you can check, I can see the number 2 maps to or pairs with -1. I can see -3 maps to or pairs with 7. The third point, I can see that 2 maps with 4. So the x value 2 showed up more than one time in my list. So that's kind of a trick or a shortcut to say this is not a relation, it's a function, because you cannot have an x value that maps to or pairs with more than one y value. And then for the last set of ordered pairs, I can see that 2 maps to 5. I can see that -1 maps to -2. I can see that 9 maps to 3. And then I can see that 5 maps to 5. So it's okay that the output 5 shows up more than once. The important thing is I'm looking at all the input or x values, 2, -1, 9, 5. They are all unique and all different. So there is not a single instance on here where an input has more than one output. So this is a function. Every input has exactly one output. Another way we can check to see if we have a function or not is by using what's called the vertical line test. And when you use the vertical line test, you're going to picture holding up a pencil or a straight line vertically, just like how this purple line is. And then you're going to slide it across the graph that you're looking at. So notice how every time that I slide this purple line across the graph, it touches the parabola exactly one time. It never overlaps or touches the parabola in more than one place. So this first example is a function because it passes the vertical line test. Now if I slide to the graph on the function on the right, graph on the right, I can see when I slide my purple line over the parabola that looks like it got turned sideways, even if I go out to the point 1, 1, the purple line is touching at the point, it looks like about 1, 1.2, but then it's also touching at about 1, -1.2. So the purple line is touching the parabola here and here. So because of that, this is not a function. It did not pass the vertical line test. And you can only pass the vertical line test if for every vertical line you slide across a graph, it will touch the graph at exactly one point at any given time. It can never touch more than once. So to look at a few more examples like this, I'm going to slide the purple line across the first graph. And notice how the purple line touches exactly one time. So it passes. This is a function. And I wrote VLT for vertical line test, but it's a function because it passes the vertical line test because it touches exactly one time. I'm going to try this graph to the right of it. It says 3 below it. Even when I start, I can see that the purple line is touching this graph at -2, 2 and at -2, -2. So this is not a function. Because it fails the vertical line test. And as I try the last two examples, I can see for 2, for example, when I start off, I'm not breaking any rules. The purple line touches the graph exactly one time. Great. but as I slide it to the right, I can see that this purple line touches the graph in 2 places at any given time. So 2 is also not a function because it fails the vertical line test. And it's pretty similar for number 4, where I start looks good, and even for this one where we end looks good, but everything in the middle of the start and the end will touch in 2 places. So for both of these graphs on the bottom, they are not functions because they fail the vertical line test. All right, some other topics we're going to cover. We're going to talk about linear functions and linear equations. When we're talking about an equation in 2 variables, it will always have an independent or an input variable and then a dependent or an output variable. And then the dependent or the output variable will always depend on what you put into the equation. A linear function can be written as y equals mx plus b. M always represents our slope. B always represents our y-intercept. Y is the dependent variable. And x is the independent variable. And I abbreviated dependent and independent, but DEPT means dependent variable, and then independent, DEPT means independent variable. M is always the slope, B is always the y-intercept, which we find at 0, and then some number. So anytime we substitute 0 in for our x value, and then solve the equation, we'll always get the y-intercept. When we're graphing, we have a few steps we want to take. Number 1, construct a table of the values. So it's always good practice to have some positive numbers and some negative numbers. So I'm going to start with x at -2, with and then go to -1, 0, 1, and 2. And the reason I like to include 0 is because then I always have my y-intercept as part of the table. We're going to substitute each of these values in for x in the equation. So we're going to solve -2 times -2 minus 2. Negative times a negative makes a positive. And so when we substituted -2 in for x, we got 2 out for y, and we can plot the point. And then we can try for the rest of the numbers, so substitute -1 in, we should get a value of 0. Substitute 0 in, we should get a value of -2. Substitute 1 in, gets -4. And then 2 in, we should get -6. Plot your points. And you don't need to keep going beyond that. You just need to plot enough points to see what the general trend or the general pattern is. So we have enough with this table to see that this has a slope of -2, it has a y-intercept of -2, and then we can connect, step 3, we can connect the points with the smooth line. And we're done, and I'm going to clean up just a couple of points because those aren't part of it. I'm sorry, I just clicked off because my pen, I don't know, it looks kind of different for me than it does for you, but that is enough information for us. So, if you have any questions, please feel free to let us know.